Okay, so in this question, we asked to find the angular acceleration of the plate, right? In the position shown, and we're told that the lengths OA and the lengths BC are parallel to each other, so they have the same angle with the horizontal, and we're given the angular velocity omega OA, right? So the approach to this question would be to solve for the angular velocity, not the angular velocity, to solve for the acceleration between points A and points B. So we can write that equation. We have the acceleration of A, which is equal to acceleration of B plus the acceleration of A relative to B. And this relative component describes rotation, right? So we can break this up into a tangential and a normal component. Cool. So when dealing with a pure rotation situation, so let's say we have fixed axis rotation, I'm going to call this point O, I'm going to call this point A. The acceleration of point A is going to be broken up into a normal component. So acceleration of A normal, and this normal component always points towards the center of rotation, right? And then we're going to have a tangential component, right? So we're going to have acceleration of A tangential, right? Now that's for fixed axis rotation, and in this case this perfectly describes the acceleration of point A. So if we were to write out our acceleration equation, acceleration of A is equal to the acceleration of O plus the acceleration of A relative to O. This becomes 0 because point O is a fixed point, can't accelerate. And then acceleration of A will be perfectly described by acceleration of A relative to O tangential and acceleration of A relative to O normal. So we can always break this component up into a tangential and a normal component. So if you remember from relative velocity, so let's say we had another fixed axis rotation case. So I'm just going to use the same example. We have VA is equal to VO plus VA relative to VO is 0. Then this breaks up into omega AO crossed with RA relative to O, right? So you can see that this describes pure rotation, okay? So the relative term in the case of acceleration and in the case of velocity, the relative term describes the relative rotation between the two. Hopefully that kind of makes sense. So in this case, we can break up the tangential. We can further decompose it, I guess. So this is going to become alpha AO crossed with RA relative to O plus the normal component, which is going to be omega AO into omega AO crossed with RA relative to O. And that will fully describe the acceleration of A. So in each case we have a term that describes the rotation of the component, right? And this shows you, it kind of shows you that the acceleration of A is purely due to rotation. Now if we had a case where it was both rotating, so we had A, and I'm just going to call this point B, And let's say that it was rotating about its center of mass G, right? So it's rotating, and it's also it also has a acceleration G, right? So I'm just gonna call this alpha G, which will be the same as alpha AB, right? And it's also accelerating in a straight line while rotating. So we can break this situation up into a pure rotation case. So we're going to have point G, and we're just going to have rotation in this case, right? And then we have point A, and then we have point B. Okay. And then to that we're going to add the translation case, where we just have the acceleration due to translation. So we're going to have point G, and we're going to have AG over here. Then again point A and point B. So since we've broken it up, we can do case 1 and case 2. So if we look at case 1 and we write the equation for relative acceleration of A and G, so points A and G, I'm just going to call this R. So if we have acceleration of A is equal to acceleration of G plus acceleration of A relative to G. And for case 1, we have pure rotation. So point G is not accelerating. So this is basically a fixed point, right? It's just rotating. It's not moving whatsoever, right? So in this case, point G is a fixed point. This falls away, and we're left with acceleration of A is equal to this thing over here, which we can decompose into the tangential and normal components, which are going to be alpha A B crossed with R plus omega AB into omega AB crossed with R. Okay, that's for case 1. And then case 2, I'm just going to do case 2 over here. So for case 2, we have just pure translation, right? There's no rotation at all. So when we write our equation, we do it again. Acceleration of A is equal to acceleration of G plus acceleration of A relative to G, right? But because this thing is moving at the same velocity, there's no rotation to it. So every single point has to have the same acceleration and the same velocity. So by default, acceleration of A has to equal acceleration of G, right? If you couldn't see that, what you could have done was again decompose it. So acceleration of A is equal to acceleration of G. This time this is not 0 because we've defined it here, right? And then plus alpha AB crossed with R plus omega AB into omega AB crossed with R, right? Since this thing isn't rotating, omega is 0 and also alpha is 0. It's not rotating. So then case 2 shows us that acceleration of A is equal to acceleration of G, right? But we can't treat these cases individually. We have to add them together. So we'll use superposition, which is basically just adding the two together. So acceleration of A, I'm going to call this total, is equal to acceleration of A for case 1 plus acceleration of A for case 2, right? Which is then going to equal AG plus all of this stuff, plus alpha AB cross with R plus omega AB into omega AB crossed with R. And this fully describes the acceleration of a point when you have both rotation, so both rotation and translation. So we're going to apply the same concept to this case over here, right? Cool. Let me just erase this stuff quickly. Cool. So we have the acceleration of B, right? In this equation, we have the acceleration of B, and we have the acceleration of A relative to B. Cool. And we can break this up. Acceleration of A is equal to acceleration of B plus alpha AB cross with R, and then, which is what we're looking for, we want the angular acceleration of the plate, and then plus omega AB into omega AB crossed with R. Right, and this R is our AB. So cool. We need to find that. We need to find, this is what we're looking for, and we need to find that as well to solve for the problem. This and this we can find pretty easily. We also don't know what acceleration of A is, right? So let's start with point A, since we know some information about this link AO. So we're first going to analyze the link AO, right? And we're first going to try and solve for omega AB. So to solve for omega AB, we need to do the velocity question. So we basically need to look at VA is equal to VB plus VA relative to B, and then this can decompose into VB plus omega AB crossed with R. So if we can find what VB is, and if we can find what VA is, then we can solve for omega AB, and then we can substitute that into our equation. Cool. So let's start with link AO, right? And they tell us that link AO has a constant angular velocity of omega AO, right? So since it's constant, we know that it doesn't have an angular acceleration. So we can add that as a little bit of info, a little extra bit of information. So we have omega, which is equal to 4 radians per second, right? And then, cool, we know that this is fixed axis rotation, so VA is going to point in that direction. You can do the velocity problem. VA is going to be equal to VO plus VA relative to O, which is just going to equal omega AO crossed with R, right? We have omega, we can get R, and we've solved for VA. So VA is going to be equal to, well, whatever it's equal to. Cool. Then, before we go on to trying to relate this to VP, we're going to do the acceleration problem. Since we already know that alpha, in this case, is equal to 0, right? Since we have a constant angular velocity, we're just going to go ahead and see what we can get from that before we move on to the next point, So we're going to say acceleration at A is equal to acceleration at O plus acceleration at A relative to O, which means that acceleration of A is equal to, this is 0 because it's a fixed point, and then this is going to decompose into alpha AO cross with R plus omega AO into omega AO cross with R, right? We have this, we have that, we have that. This is 0 because it has a constant thingy. It has a constant angular velocity. So that will be 0, and then, cool, we've solved for our acceleration of A. Right, so even though we have a constant angular velocity, it doesn't mean that a point on this line, right, this line AO, doesn't mean that points on that line have 0 acceleration. It will have a 0 tangential acceleration, but it won't have a 0 normal acceleration. Okay, so you might not understand this, and that's fine. But to visualize a point traveling on a circular path, let's say you have point A, which starts over here, and let's say that this is the center of this arc, basically. So I'm going to call this center O, and A has, it starts off with the velocity that's perpendicular to the radius, right? Cool. So this is at T1, okay? So at T1, it has a velocity like that, okay? Then at T2, if I draw point A at another point in time, you can see that its velocity has gone from looking like that to a slightly decreased value. So like the vector is now pointing more to the horizontal, if that makes sense. The angle has changed. In order for a velocity to change its direction or its magnitude, you need to have some acceleration, right? So that's the normal acceleration that's constantly forcing the direction of the velocity to change. And at another point, we'll call this T3, the velocity of A is now perfectly horizontal, right? And the thing that's causing it to do that is the normal acceleration. So you can see the normal acceleration is pulling the velocity vector downwards. So it's constantly pulling it downwards, right? Constantly pulling it towards the center. So yeah, hopefully that makes sense. So if ever you have a point moving around a circle, just know that even though its velocity might be constant, its acceleration isn't. Its acceleration is the thing that allows it to keep changing its direction, but it doesn't affect the magnitude of its velocity. Cool, I hope that makes sense. And then, yeah, we've solved for acceleration of A. We've also solved for its velocity. So let's then go and look at the velocity of A and do that relative to the velocity of B, right? This is then going to become VA is equal to VB plus omega AB times R, right? So we don't know what VB is and we don't know what omega is. So let's try and draw a triangle and see if we can get anything from that. So I'm first going to draw a link AO just to get the direction of VA, right? So this is theta. And then I'm also going to draw link BC. And then this angle is also theta. And B can either go that way or that way. We're going to assume that we don't know the direction of phi B. And then if we draw in AB, the line that connects points A and B, we know that the relative velocity is going to be perpendicular to this line, right? So this is phi A relative to B. Could either go up or it could either go down. We aren't sure. Then let's try and construct a vector triangle using this information. So I'm going to draw in phi A first, and I'm still going to take note of my equation. Phi A is equal to phi B plus phi A relative to B. I know that phi A must start at the tail of phi B and end at the head of phi A relative to B. So I'm going to draw in the vector that I know the most information about, which is phi A. I'm going to draw that in this direction. And I know that phi B must start at the tail. VA must start at the tail of phi B and end at the head of phi A relative to B. So VA must start at the tail of phi B, and phi B could either go this way or it could go that way. Right? And phi A relative to B could either go up or it could go down, right? And we know that VA must end at the head of VA relative to B. So it's basically gonna start, if I draw this properly, it's basically gonna start and end here, right? Which it's 0, right? It's not gonna equal anything. Reason why is because VB, we've already met our, or followed the rule that we set out, I guess, where VA has to start at the tail of VB, right? So it starts at the tail of VB and it ends at the head of VA relative to B. And VA relative to B, since it's a vector that goes up, it's just going to be this point over here, which is 0, since VA and VB are on top of one another. So this tells us that, let me just draw it like this. This is VB. So this tells us that VA is equal to VB, right? Which means that VA relative to B is equal to 0. So whenever you have a case like this where you have two links that are at the same angle with one another, then there won't be any relative velocity between the two. So if you have two links and you have a body in between, VA will always equal to VB. But you have to show why that's the case. You can't just write down that VA is equal to VP, right? So since VA relative to B is equal to 0 and VA relative to B is equal to omega AB crossed with R, right? Then that means omega AB crossed with R is equal to 0, and this can only be true if omega AB is equal to 0. The distance R between the 2 points can't be 0 because there's a set distance between the 2 points. It's not like you can squish the points together and make that distance 0. It's a set distance that's there. So the only way for this to be true is for omega AB to be 0. Cool. Then coming back to our acceleration equation, we can then cross out this term because omega AB is equal to 0. Then we only have 2 terms, well, 3 sort of. We've now solved for acceleration of A. We're just left with the acceleration of point B and then the angular acceleration which we're trying to solve for. Okay, so to get the acceleration of B, we can say acceleration of B is equal to acceleration of C plus acceleration of B relative to C. And since C is a fixed point, so okay, I'm just going to draw that link in just so that it's easier for you to see what's going on. So we have point B, point C. C is a fixed point. And then this is going to decompose to alpha BC, right? Times R plus omega BC into omega BC times R, right? So we don't know this, right? We don't know omega BC, and we don't know that, and we don't know that. So we have 3 unknowns and we have 1 equation, but we do know that VB is equal to VA. And we can solve for VA because we're given the angular velocity in that link. So we can do the velocity problem for link BC. So we have VB is equal to VC plus VB relative to C. And then that will decompose into omega BC crossed with R. That will give you VB. And then we know this because we know that it's equal to VA. Then we can solve for that. And we also know that. And then we can plug in our this is omega BC. Can plug that into this. And then we'll get that acceleration of B is equal to alpha BC crossed with R plus omega BC into omega BC crossed with R. And we know what this is, we know what that is, we know what that is, we know what that is, we don't know what that is, right? Which is fine. So we plug this back into our big equation, and then we get acceleration of A, which is equal to the acceleration of B, but we're just going to substitute all of this for that. So I'm going to get alpha BC crossed with R plus omega BC into omega BC crossed with R, right? This represents the acceleration of B, then plus all of this stuff. So remember, this term fell away, so we're just going to write alpha AB crossed with R. Okay, now we know that value, we know these 2 values, we don't know this is what we want to solve for, and we also don't know the value of that. So what we'll do is we'll decompose everything. So we're going to get acceleration of A, the magnitude of the acceleration of A, and then it will have its I component and its J component, and that will equal alpha BC, and then whatever this gives you in its I component and its j component, right? And then plus all of this, which will give you an I component and a j component, plus whatever this gives you. So we're going to have alpha AB into an I component and a j component, right? So this we don't know, that we don't know, but we know that. And if you write an equation for the I components and for the j components, you'll get two equations with two unknowns, and you'll be able to solve for alpha AB.